Our next presentation is effective verification of stacked and layered protocols. Ofir Michaeli of Cadence. Ofir is a verification engineering manager leading the MIPI, MFI, and Unipro verification IP and JEDEC UFS memory model development at Cadence. He is vice chair of the MIPI Unipro working group. He holds a BSc in computer science and mathematics and is an MBA candidate at the Hebrew University of Jerusalem. Ofir Michaeli. Thank you.
Hi, everyone. So first of all, I'm really glad to be here and discuss pre-silicon verification. So as Roy said, I'm working at Cadence for quite some time, and the past 6.5 years, I'm doing pre-silicon verification of MIPI protocols. I'm leading the development of the MIPI M5 family protocols like M5, Unico, DiGRF, LLI, and CSA3, and also the JEDEC UFS memory model. With that, I want to mention that, there is no such a thing as perfect design, and even if you do create some certain tests and you think that your design is quite good, you can never be sure unless you verify that you actually cover the entire spec and you have no holes in your verification. And even if you do get to 100% coverage, you can never be sure that the protocol itself is flawless and has no deadlocks or bugs. And with that, I want to encourage everyone here which is not a MIPI member to join MIPI, and those of you who are MIPI members to join the working group activities. In that way, you can ensure that you actually understand the protocols the best, and you can actually influence the way the protocols are written and influence the protocol roadmap and help us make them better. So this is the MIPI framework. There are a lot of MIPI standards, but in my presentation, I'm going to focus on MFI and Unipo and UFS. And I'm going to explain a bit what are these protocols and what is pre-silicon verification, why pre-silicon verification is so important, and I will end with some tips which I think that are most important to have good, an efficient and effective verification of any MIPI design. So I will start with MFI. I don't see the notes. So MFI is a very mature protocol. It's been around since 2010, starting with MFI 0.8. And it's a bidirectional protocol. It uses the 8-bit, 10-bit encoding, which we are all familiar with. And it's quite fast. M stands for 1000, which is 1000 better than the rest of the PHYs that MIPI provides. Currently, the current M5 version is M5 4.0, and the working group is working on M5 4.1, which will be available soon. But I think that the most used M5 version is M5 3.1. So M5 is quite simple. Once you get to know it, you know exactly which features you need to use among all the available features that M5 provides. It's quite simple, and it has a very well-defined upstream and downstream interfaces. Next is Unipo. So Unipo is a stack layer on top of M5. It's designed to resemble the OSI model. So it has a PHY adapter layer that connects Unipo to M5 and the medium. The PHY adapter is responsible for detecting the link, managing the power. It has a PCP protocol for exchanging capabilities and configuring the link. It has EMI capabilities, EMI reduction capabilities, and a PHY test feature to actually test MPHY. Above that, we have the data link layer, which is responsible for exchanging the data frames. It has a control frame mechanism to exchange credits, a replay mechanism to ensure that all the data is transferred in the right order and nothing is lost. We have the network layer, which is responsible for managing the network in case a network is used, and the transport layer, which is responsible for the connection with the application, managing the virtual channels, and it also has a test feature allowing to test the entire Unipo stack. So Unipo, as well as MPHY, is very mature protocol. It's also around for quite some time, and the current version is Unipo 1.6, which bounds to MPHY 3.1. And the working group is currently working on version 1.8, which will be available in the upcoming months. So despite of what everyone thinks, Unipo is actually used in the industry, and it has a vast infrastructure support. Besides the protocol, it also has few application notes with Q&A that describes what stood in our mind when we decided to develop a certain feature and why we decided to design it that way, or any questions that developers encountered and we helped them solve, implementation issues, all are explained in the application notes. We also have a CTS, a conformance test suite, which is well used by Unipo developers and also in our interoperability events. Interoperability events, of course, we already had 3 such events where actual developers coming with their device and try to connect their devices and run tests against other developers' devices. The last interoperability event was last year in Hsinchu City in Taiwan. And actually the next IoT event is going to be next month, just before the next MIPI face-to-face. It's going to be in Taipei this time. And actually there are a lot of IPs, VAPs, text equipment, and protocol analyzers already available in the market, and you can see actually few of them in the demo outside. So the key features of Unipo that I think are the most important are the fact that Unipo has a low print on power consumption and PCB area. It's bidirectional, unlike other MIPI protocols. It allows basically to write and read data at the same time if you're using UFS, or to configure the camera and also receiving images at the same time if you're using CSA3, for example. It's application agnostic. It doesn't care what data you transmit. It's the transport layer, and it will make sure that all the data is transferred. It's very easy to use. It has a lot of features. Not all of them are required. Once you know which features you need and you read the spec, it's really not that complicated like people think. And of course, it has a guaranteed and in-order delivery of payload, which is the most important part. And last but not least, UFS, which stands for Universal Flash Storage, developed by JEDEC. It's basically built on the eMMC heritage. It's not competing eMMC. It's being developed by the same people in the same task group in JEDEC, and it's supposed to be better. It's a high-performance storage interface designed to use in computing and mobile systems requiring low power consumption, like smartphones, tablets, drones, or anything that comes into your mind, like IoT equipment and things like that. It's using MIPI, MPHY, and Unipo as the transport layer, which allows basically high speed and low energy consumption. And it's using the SCSI command set, which is used by a lot of storage protocols, and we are all aware of. Okay, so what is pre-silicon verification and why do we need it? So during the pre-silicon process, the engineers basically test their devices in a virtual environment with sophisticated simulation tools and softwares. They are designing a VAP or buying a VAP, connecting it to their own device, creating a test bench and configuring the test bench and the VAP, and writing tests. And basically, the VAP takes those tests and stimulates the DOT, and also observe all the data which is sent by the DOT back to the VAP, perform protocol checks, make sure that the DOT is compliant with the spec, and also collects coverage to show us visually what was tested, what was not tested, where we have coverage holes, what else we need to test, and basically allows us to go and write more tests, create different test suites, and continue on and on, creating more tests, stimulate the DOT, and making sure that we get 100% coverage. So we saw what is pre-silicon verification, and now let's see why pre-silicon verification is so important. So I'm not going to tell you again why it's important to catch bugs in pre-silicon verification, because you can actually save a lot of time and money if you find bugs in pre-silicon verification and not in FPGA or in silicon. I'm going to basically explain real challenges that we came across when going to verify MFI, Unipo, and UFS. So the first challenge is that we have a lot of interfaces. I will go into more details in the next slides, but we saw that MFI and Unipo define very well the upstream interface and the downstream interface, and it's essential basically to make sure that it all works properly. If you're buying some third-party IP or designing it in another team, it's very important to make sure that you're interoperable and talk the same language with the other device. So in that term, we have the RMMI defined in MFI. We have the C-port interface defined in Unipo, which is used to connect to the application layer. And we have the DME interface. Another challenge is basically the backward compatibility. MIPI specs change a lot. We get almost a new version for each protocol every year. So it's a good thing. We are getting new features, we are fixing bugs, but it's very important to make sure that your new device can still work with older devices in the market, as well as while still working on your new device, you want to make sure that it can already communicate with other devices in the market. So if we take, for example, Unipo 1.6, you want to make sure that your Unipo 1.6 device can still work and connect with other Unipo 1.4 ones. But in a few months, we will have Unipo 1.8, and if you don't have Unipo 1.8, you still want to make sure that your Unipo 1.6 can still be connected to a Unipo 1.8. Another challenge is verifying new features or features that change between versions. And we can see a few examples like scrambling, which was introduced in Unipo. So the same algorithm is used to scramble and descramble, and we saw customers that came to implement this new feature and implement it wrong, but they thought everything is okay, and once they started doing the verification process and connected to our VAP, a third-party VAP, they started noticing that things are not working as expected. And features that change between versions, for example, adapt state in Unipo 1.4.0 will change in Unipo 4.1, and you want to make sure that it's working properly, that you understood all the changes, and that your design is perfect. Another challenge is unclear or features which have vague description. For example, the deep save state in Unipo 1.6. So it's a great feature. It is described in the spec. We did explain what happens when you go into deep save state, what should happen when you leave the save state. But one thing that is not mentioned in the spec is how you make the application control this state. How do you make the application tell Unipo to go into deep save? And it's a verification challenge. And we are going to change it in Unipo 1.8. We are going to explain that. But for all Unipo 1.6 devices out there, it was a real challenge to make sure it works properly. Different companies implemented it differently, and we found out in the interoperability event that we should probably fix that. And another very important challenge is running with different configuration or with different set of supported features. So if you're developing some FPGA or silicon, and you can always connect it back to back and make sure that it works. But how can you be sure that it will work properly when you connect it to a third-party device? How can you be sure that the other device, which has a different set of supported features, will manage to finish link initialization and capability downgrading correctly? And during the verification phase, it's essential to make sure that you do test your device with all the different sets of configurations, all the different sets of capabilities to make sure that your device is capable of doing that. Sorry. Okay, so let's have a look at a few challenges in more details. So in Unipo 1.6, for example, a new PCP frame was introduced, PCP cap X1 indication, which allows the two sides to exchange some more capabilities. It has an older brother called PCP cap IND. And basically, what's important is that when you're going to actually develop a Unipo 1.6, to make sure that when you're connected to a Unipo 1.41, for example, that doesn't know this PCP and doesn't send it, that you are still able to finish link initialization correctly. And to make sure that if you are getting a malformed PCP like that, that you know to drop it, and you can still work as expected, and link initialization ends. Another feature that was introduced in this PCP frame is the ability to let Unipo bypass the MFI line config state. And before that, it was mandatory. And in Unipo 1.6, we allowed customers to basically bypass this state. And it's essential to make sure that once those frames are exchanged between the local and peer devices, that your device can actually understand that the peer doesn't require going into line config, doesn't require getting the LCC read commands, and that you can bypass line config. And to make sure that if the other side doesn't even support it, that you are not going into line config and crashing. Okay. And the next challenge I want to deep dive into is the different interfaces. So I did mention before that those protocols have very well-defined interfaces, but as any other protocols, we also have some issues. So the RMI interface, which is defined in MFI, it's optional. Not everyone has to implement it, but if you do implement it, you must do it based on the spec. So we did see some third-party companies implementing RMI differently. Some companies required some additional information from the entire SoC, so they introduced new pins, or their current pins behaved a bit differently. And when going to integrate those MFIs, let's say you are developing a Unipo device and you want to integrate to such an MFI, if you don't have those pins, it will not work. So it's essential to understand what is required by the third-party IP that you are using and what is required by your own device. And Unipo doesn't define the downstream interface with pins. It refers to RMI, and it has its own SAP definition of downstream interface. SAP stands for Service Access Points. So it's very important to understand the matching between the Unipo SAPs and the MFI signaling interface, the RMI, to make sure that you understand how it should work and connect MFI and Unipo correctly. The CPORT interface in Unipo. So it's also in an annex in Unico. It's also informative, so you don't have to implement it, but if you do implement it, it must be like described in the spec. But I think that the problem here is that Unico defines two different C-port interfaces. We have the multiplexed and non-multiplexed interfaces, and it's essential to make sure to verify that your interface works as expected based on the spec. And the last issue with interfaces is the DME interface, which is defined entirely with subs. There is no DME pin interface defined in the spec, and a lot of customers are doing different things. Some implement it with pins, some implement it with registers, and it's very essential to make sure that it works properly. Okay, so I think that's going to be my only marketing slide. I'm not going to talk about Cadence. I'm going to explain about VAP and why you should prefer buying one. So why do we even need a VAP? Why not just creating some simple tool that can create vectors of data and stimuli our DOT? It's not enough because then you waste a lot of time on debugging, understanding the waveforms, and you can get a lot of more information from a VAP. A VAP is a software-based. It's a software which checks for protocol compliance based on the protocol specification. It provides also a full coverage model that allows you to see what was tested already, what's not tested, and what else should be checked. It generates and drives test sequences. So basically you can create a very small building blocks sequences that look like data frames, control frames, and so on, and then reuse those building blocks in other sequences, other scenarios, other virtual sequences. You can reuse the same sequences in your verification of newer versions of your design, or also in the SOC environment. And I think that the most important part is that it's flexible, it's software. You can introduce new pins in seconds, you can add whatever you need, you can add new features, you can remove features. It has no vendors specific capabilities, so you can configure it the way you want, make sure it works with create one test with a certain capabilities and settings, a different test with a different capabilities, and make sure that your device is working properly. And usually it's being developed by an independent team, either within your company or a third party, and it ensures that someone else looked at the spec, probably understood it a bit differently, and you can find a lot more bugs that way than just connecting back to your own design. And as I said, why you should prefer buying one and not making one? So a VAP is much more complicated than a real design. It has, it speaks the spec language, but it also knows to introduce error injections and error scenarios. And it also observes what the device under test sends. So it doesn't only behave to what the device sends, it also provides protocol checks and give you information of what was right, what was wrong, where you have having issues. And it also provides coverage, allowing you to know what was tested and what not. So it can take sometimes many years of development. Another thing is that if you created your own VAP, verified your own design, but tomorrow there is a new version of this protocol, so you need to invest creating the new design, but then you need to go and recreate the VAP. And with a third-party VAP, you usually get all that for free. New versions, new protocols are supported. And another reason for using a third party is that usually it's being tested by other companies as well. So you're sure that this VAP is working properly. You are not wasting time on debugging. If you have an error, debugging the VAP as well as the design, you usually get a better VAP that was already tested by other customers. And if there are any bugs in the VAP, they were probably been fixed already. Okay, so we saw already what are the protocols, what is pre-silicon verification, and why we should do pre-silicon verification. And now I'm going to touch a bit how pre-silicon verification should happen. And I'm going to give you some tips on how to have a better, effective, and efficient verification environment. So a verification should happen in few stages. First of all, you create a verification plane. You decide whatever you want to verify, how you want to verify that. Then you create a test plan. You decide which test you want to perform, which tests are redundant, which tests are checking features that you're not going to support and you don't need to write them. Creating the verification environment and test bench, running the actual tests and debugging if something is wrong, and eventually collecting coverage and analyzing the coverage to see if you need to do any more testing. So my first tip is that verification should start as early as possible. And as early as possible means that you should start doing your verification even before you have the design. How can you do that? So first of all, the spec is usually available. What we recommend is taking the spec, analyzing the spec, understanding what the key features are of the spec, analyzing what you want to verify, what you need to verify, how you want to verify it, and start creating the verification environment. The way I usually recommend is starting creating the verification plan by going over the spec and marking each sentence in the spec that I think that should be verified and actually linking it to a verification item in my verification plan. And then later on, once I already have the VAP ready, and with the coverage model, I also link the verification items to the coverage items. And once the tests were executed, I can see that if a coverage item was not collected, I can go back to the verification plan, to the verification item, and see the exact sentence in the spec that is related to that. Okay, so after we created the verification plan, the next thing is to go and write your own verification IP, writing your verification environment, and starting writing tests. And my next tip is that it's very, 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 very essential to understand what you want to test and how to test it. And if we are looking at the Unico spec, for example, it's never easy to understand how much testing is enough, how much is too much. You don't want to waste resources in testing things that are redundant, are not going to be used, are not even supported in your VIP. And if you're looking at a Unico spec, the PA Hibernate description is 3 pages, which most of them are figures, showing how the Unico device should go into Hibernate, how it should behave in Hibernate, and how it should exit Hibernate. So going over those pages, I easily identified 32 test scenarios, but with all the different configurations, different speeds, gears, series, termination, whenever you, the time when you go into Hibernate, what happens if you are going into Hibernate and there is a reset, what happens if you go out of Hibernate and there is a reset, and so on and so on. You can easily get to thousands of test cases. And it's not sure that you need to run all those scenarios. For example, let's say you're going to verify a UFS card which supports up to high-speed gear 1. There's no need to test scenarios of trying to switch to high-speed gear 3 or things like that. Okay, so the next tip is you should wisely choose the verification language and the methodology that you are going to use. There are a lot of different verification languages, different methodologies, System Verilog, UVM, OVM, VMM, and so on. And it's important to understand how your current environment is going to look like, so you'll be able to choose the right languages, but it's also important to think about the future. If you're going to have later on an SOC environment which is written in SV, UVM, not so wisely to pick SVOVM right now. In my perspective, it's very important to choose languages that can be reused, like E and System Verilog. And in that way, you can write your own sequences for your current environment. And then when you're going to SOC environment, you can actually reuse those sequences. You don't need to write new environment, new tests. You can just reuse it. Next tip, verify all the interfaces. So, as I said before, there are a lot of interfaces only in those three protocols, and I'm not talking about other protocols, but it's very important to check all of them and check that all of them are working properly. Even during your implementation, you don't need to have the entire MFI Unipo UFS stack to start verifying. You can start early. Let's say you are creating a Unipo DOT, but you only have the PHY adapter or DL layer right now. You can already start verifying with a Unipo VIP and an MFI emulation connected to RMMI to make sure that it works. It's important to make sure that the Unipo VIP can work that way, because if there will be also a TL layer, then transmission sent from the Unipo DOT, which has only DL layer, will be identified as an error in the VIP. So in that way, you can choose only the layers that you already support in the DOT, and that way the data will be correct. Once you finish creating your Unipo DOT, but you don't have an MFI yet, or UFS yet, or you just want to make sure that they are working properly, you can connect your entire Unipo DOT to an MFI and Unipo to make sure that the Unipo works well. And if it's a Unipo that will, in the future, will connect to a UFS host, for example, you can connect also a UFS memory model on top of Unipo, and on the other side of your DOT, on top of the C port, connect a Unipo application layer that can generate UFS host-alike transmission and verify your Unipo DOT that way. In case you already have a UFS host as well, you can just remove the Unipo application VAP layer and verify your entire stack. And if you have also MFI, you can verify everything on top of the serial link. And with that, also, if you have only MFI, or you want to verify that your MFI is working correctly without Unipo and UFS, you can connect your MFI to an MFI VAP on the serial link, and to an MFI RMI VAP on top of the RMI link, to make sure that MFI interfaces are working properly. Okay. Next, use a passive agent. So in Cadence, we encourage using passive agents, and a lot of customers keep asking me, what do we need passive agent? Why cannot, it's eating performance, why can't we just use an active agent and stimulate our device under test? So, So it's very important to understand that there is a difference between an active and a passive agent, and they have different objectives. The active agent is purely talking the spec. It knows to create stimuli based on the customer tests and drive them to the DOT. And it also observes the link, see what the DOT is sending back, but it behaves according to what the DOT sent. For example, if the DOT is sending frames with CRC error, the active agent will not report any error for that. It will collect the CRC error and send the NAC for that, like any other device behavior should be. The passive agent, on the other hand, it's actually monitoring the lines, monitoring the device under test, and provide protocol checks. So let me go back to the active agent for a second. So the active agent can be configured with any configuration, any settings, any capabilities that you like, different capabilities per test if you like, to make sure that the device under test works properly. The passive agent, on the other hand, must be configured the same as the DOT. The DOT is a black box for the verification environment, and by configuring the passive agent with the same configuration as the DOT, basically what we do is we emulate what's going in the device under test, and we predict what will be the device under test response. And if it's different, we fire an error for that with information of what we expect and what was sent instead. Except protocol checks, the passive agent also provides full coverage model, and then once you run tests, you can see what was tested, what was not tested, understand which features were tested already and what else you need to test. Another tip is invest in tools. Invest in tools not necessarily in money, also in time. It's very important to understand exactly what you need in your verification process and make sure that your tools provide it. I hate wasting time on analyzing waves if I can have more details. So here we have some examples of different tools. For example, logs which have colors exactly as the colors in the spec. Unipo spec has different colors for each layer, so it's really easy to identify which lines in the log belong to the PHY adapter, which to the DL layer, which to the TL, and so on. And you can also later on filter only the sentences in the log that are relevant to what you are debugging. Also on the waveform, no one likes analyzing waveforms, trying to count the number of bits in high speed to make sure that the marker 0 was received correctly. So it's a bit hard to see here, but if you download the presentation, you will be able to see it. So here you can see that the VAP is actually collecting every 10 bits and creating MFI symbols out of them. So it's easily, it can be easily debugged, and you can see whether the VAP identified the 8-bit, 10-bit symbols as expected, and have the right trackers. So here we have an example from the Unipo spec of the PCP cap indication, and here you can see a symbol tracker showing all the symbols that were collected by MFI, and here a frame tracker that was created by Unipo with the same structure of the frame in the spec, all the fields. You can also see it graphically and get all the information of each frame, each field. You have the field name on top, right, like in the spec, and the value that was collected. And by using the right tools, you will save a lot of time in debugging, understanding what happened in the spec, learning the spec. Sometimes we get integrator customers that are buying 2 third-party IPs, one MFI and one Unipo from different companies. They don't know the specs very well. They are developing UFS. Why do they care about MFI and Unipo? But only with the right tools you can actually analyze what was tested and understand the errors that you see. And I think that the last tip I have for today is always make sure that you're covered. Always make sure that you have good coverage model of the protocols that you are using. Always make sure that everything that you want to see that been tested was actually collected in the coverage. See which holes that you still have in your coverage, rewrite tests or write more tests, and keep on verifying, making sure that everything works correctly and perfectly and that you have no bugs. So with that, I want to encourage you to come to the demo area. If you have any questions about MFI, Unipo, UFS, or any other MIPI protocol, you're welcome to come and ask, and I will gladly answer anything. Thank you very much.
Any questions for Ofir? No questions? Clear as mud. All right.
Okay.
Ofir, thank you.
Thank you very much.